In this lecture, what I'd like to talk about is some events that occurred in the 80s, the early mid-80s, and these really put nanotechnology on the map. We previously heard about Richard Feynman and Drexler and so on, very much theoretical concepts, but the things that put it on the map were essentially two experimental developments. The first was a form of carbon unknown to man. We only knew two pure elemental forms of carbon up until the mid-80s. The other was that we had never been able to truly see individual atoms in real space, image them, and also, in addition, manipulate them, move them on a single atom basis. And this was due to two developments: the development of the scanning tunneling microscope and the discovery of the thing called the buckyball. And let's begin. Okay, in this part of the talk, what I'd like to discuss is different ways to connect up atoms. We all know that if we connect different types of atoms, we form different types of compound, and the chemical industry is based on that type of principle. However, there are cases where you can connect atoms up in different ways. For instance, before 1985, carbon had two what are known as allotropes, diamond and graphite. So you know that diamond is very clear, very hard. It doesn't conduct electricity. And you may be aware of graphite, for instance, with a pencil, which is a mixture of graphite and clay. And graphite is a very soft material, it's black, and it's an electrical conductor. Well, in 1986, three scientists, Rick Smalley, Curl, and Crotto, they discovered a new form of carbon that had never been known before. This is just pure carbon, and it contains 60 carbon atoms. And they received a Nobel Prize for their work. And people also discovered other ways to connect up carbon in the form of tubes called nanotubes. And in fact, the 2011 Physics Nobel Prize went for another type of material, which was just a single sheet of atomic carbon known as graphene, not graphite. And there is a great deal of interest in these materials because they have never been known to mankind before. So let's look at diamond. Diamond is a girl's best friend, they say. Pure carbon atoms, transparent, hard. Graphite, it's a layered material, black, shiny, conducting electricity, and also conducting heat. When we look at the geometries of connections in diamond and graphite, we find they're very different. For instance, on the top right, you see graphite, and you can see the sheets contain hexagonal structures connected like a honeycomb structure. And the honeycomb structure is in layers, and the separation between the layers is quite large, such that these layers can slide across each other, hence the way the pencil lead works when you draw. On the other hand, if you look at the diamond structure, and that's shown on the left in this ball and stick model, it consists of a tetrahedral structure. And tetrahedral structures are very strong, and that gives it its strong structural capabilities. Now, in the case of the buckyball is shown in the bottom right, and it contains the 60 carbon atoms arranged in both hexagons and pentagons, such that no two pentagons are actually face-to-face against each other. It's called isolated pentagon rule. And that is basically the structure that was discovered in the 80s for this new form of carbon. This new form of carbon actually came from studies of extraterrestrial space, where people observed certain signals, chemical signals in spectroscopy, and they knew there were 60 carbon atoms, but they didn't know how they were interlinked. And in fact, both Smalley and Crotto were trying to figure this out when they recalled the fact that an architect and futurist, his name was Buckminster Fuller, had created these structures using different materials as architectural forms, and he called these things geodesic domes, and they were very popular in California, for instance, in the late 60s in the hippie movement. So they were inspired by Buckminster Fuller's work, and they soon realized that this structure has this soccer ball-like geometry. In terms of mathematics or geometry, you would call this structure a truncated icosahedron. A little bit later, Ijima, who was working in Japan at NEC laboratories, he discovered also in the kind of soot that remained after people passed a carbon arc, an electrical current through carbon electrodes, he also discovered another structure which was called the carbon nanotube, and that's on the bottom left. And these tubes actually consist of hexagonal sheets, similar to one sheet of graphite, but they're completely rolled up and they connect together. And there are different ways to connect them. There's a whole family of different forms of carbon nanotube. But the carbon nanotube was found to be stronger than steel and much lighter, and it's actually the basis of Arthur C. Clarke's space elevator, which he proposed in one of his novels. Now, it's important to remember when we deal with these molecules that when we look at a picture of a molecule, we're not actually looking at how the molecule really looks. In other words, these different representations here are representing something that is invisible. And we can represent the atoms by balls, we can represent the connections by sticks, we can represent the electrons by larger spheres called space-filling models, or we can take hybrids of one model and another model and in a computer generate a picture. But the picture is not really a representation of the molecule. The molecule is essentially, in a way, invisible. It's more like a cloud of electrons and probabilities. Now, that was the case until around about the early 80s. In fact, this year is the, I think, the 25th anniversary of the discovery of a beautiful machine called the scanning tunneling microscope. And it was invented by a German and a Swiss scientist, Gerd Binnig and Heinrich Rohrer, at the IBM research laboratories in Zurich. That's where I started, actually, in 1983. And this invention was so important that they received the Nobel Prize for Physics in 1986. So what is this microscope all about, and how is it different from other ones? Well, regular microscopes use lenses, typically. They use lenses to focus light and magnify objects. But the magnification of the microscope is limited. It's limited because of the wavelength of the light, which is on the order of hundreds of nanometers. On the other hand, scientists had developed things called electron microscopes, but they use very high energy electron beams to generate wave-like characteristics on the subatomic scale. However, they damage the sample and require a vacuum. The scanning tunneling microscope is a radical deviation from that approach in that it feels the surface. So in this photograph here, you imagine that the scanning tunneling microscope is your finger, and you're feeling the atoms represented by balls here, and by tracing over the surface laterally and feeling the surface, you can then map out the position of the atoms. The finger is actually a needle. This is a tungsten needle, which is terminated by a single atom. And one can approach the surface, and by using very advanced technologies, you're able to maintain the position of that tip above a surface to win about 1/100th of an atomic diameter. And here in this video, we demonstrate the basic principle of the scanning tunneling microscope as it rasters across the surface. The rastering process is something like the way a television works, the electron beam in a television, an old-fashioned television, I should say, cathode ray tube-based television. And you can see here how the surface is mapped by the scanning tunneling microscope tip being rastered. Now, this rastering process shown in step 1 is then converted into an image, a very simple image, which is shown in number 2. So it's a grayscale. The higher the tip, the more white it is. The lower the tip, the darker it is. And then in the computer, we can convert that into a mesh contour map, and we can also then color it. And then if you look at the bottom sequence, what we've done then is added some shaded illumination and color and so on, and we can end up with a beautiful pseudo three-dimensional representation of the surface. The first surface where one could resolve atoms, and really what put the thing on the map, was a thing called the silicon 7x7 reconstruction. So the surface of silicon undergoes a very complicated structural transformation when heated, and it forms a situation where you have some atoms, extra atoms on the surface, you have holes in the surface in a geometric pattern. And this could not be solved using the physics techniques of that time, but the scanning tunneling microscope enabled people to actually visualize this in what they call real space, because up until that point, people on the atomic scale worked in inverse space. It's rather unintuitive, but it's how they had to work. So in real space, you could see the position of every atom, and this silicon 7x7 surface is shown on the right in terms of the pseudo-illuminated 3D model. In the center is the raw data, that is the height, and on the left is actually a theoretical model of the reconstruction, which matches perfectly with the scanning tunneling microscope data. Another thing about the scanning tunneling microscope, in addition to the fact it could see atoms, is the fact that it wasn't limited to vacuum. Most things in life are not in a vacuum. Most of life is actually in a fluid, and the scanning tunneling microscope was able to resolve atoms in air, in liquids, at very low temperatures, like liquid helium temperatures, close to absolute 0 Kelvin, up to 1,000 degrees. And also in environments like a battery environment, that's called an electrochemical environment. But it did require that the surface be electrically conducting. That meant it was somewhat limited to metals and semiconductors like silicon. However, if you put a molecule on the surface and it's a conducting surface, you could also image it. So let's look at some nice pictures with the scanning tunneling microscope. This is a low temperature picture of copper at 4 degrees Kelvin. And what you can see are a series of steps and terraces. And each of those steps is 1 atom high. And on the terrace at this low temperature, you can also see what looks like waves. You can see wave patterns. And this is actually quantum mechanical wave patterns of the electrons. They're called standing waves. It's a bit like when you drop let's say, drop a pebble in a pond and you see beautiful wave patterns propagating. The scanning tunneling microscope was also able to do something that had never been done before. And that was, if we bring two atoms together and they like each other, they form what is known as a chemical bond. That's a stable bond. Well, with the scanning tunneling microscope, we could bring the atom very close to another atom, and we could actually tune a chemical bond. So we could make a partial chemical bond, and we could release that chemical bond. And this effect was used to manipulate atoms, because if we came close enough, we could drag an atom across the surface. The first person to do this was Don Eigler. However, here is an example of UCLA written in single carbon monoxide molecules by Lisa, who was a graduate student in my group. And the most amazing thing about this is that it's stable. You can leave it there for days. It took her 2 days actually to build this, and she had to learn a lot of skills to just generate the environment for such an experiment. My colleague Don Eigler, who was at IBM at the time, he made even more fantastic structures where he used the atoms to manipulate the surface such that you could make standing wave patterns. And what you see here are atoms which have been rearranged into a hexagon, a triangle, circle, and a square. And you can see how, depending on the shape, the patterns of the electrostanding waves change. In particular, the circular one really resembles something like a pebble being dropped in a pond. Other things you could do with the scanning tunneling microscope, and this is fairly recent, is actually take a molecule and solder molecular wires to it. And this is a representation here where we have on the left a kind of model of the scanning tunneling microscope tip tunneling on a chain of molecules which are polymerized. Once you initiate this polymerization, then the molecules will start to propagate along here in the polymerization process until they hit a molecule and make a molecular wire. And this was just achieved basically in the last year. So when we run this movie, it's more or less obvious. This is a model. You can see the molecules called copper phthalocyanine. We bring in the tip, and now we start the polymerization process. And this is a chain polymerization, so we have to initiate it once. It's very interesting for nanotechnology because we use a kind of self-assembling type of process to initiate reactions that allow us to polymerize a single molecular chain as long as it's free to continue it unless it hits a defect, or in this case, bonds to a molecule. So that's wiring a single molecule. Now, another development in the scanning tunneling microscope field was how do we look at surfaces that are non-conducting? And the solution came in 1986 when Carl Quate, Christoph Gerber, and Gerd Binnig discovered a new type of variation of the tip technique called the atomic force microscope, or AFM. The atomic force microscope relies on measuring the force between the tip atom and the surface. As an example, you imagine if we approach a tip to a surface, there is initially an attractive force, but when the atoms touch, there's a repulsive force. So one can balance those forces, and by fine-tuning the force and keeping the force constant, you can also map out a surface similar to the way you would use your finger at. The kind of resolution this type of non-contact atomic force microscopy was able to achieve is quite amazing. There's a whole field of atomic force microscopes used in industry to inspect things, but this particular one, a particular form of atomic force microscope called the non-contact atomic force microscope was actually able to image molecules in a way that hadn't been achieved before with the scanning tunneling microscope. So for instance, if we look at this structure which is on the bottom left, what you can see is a chemist's drawing, like Kekule's dream of benzene, for instance, was of hexagonal structure. And this molecule is called pentacene because there are 5 hexagons in it. And what you see above is the atomic force microscope picture, which has been, I must say, image processed in many ways, but the resemblance between the AFM picture of the molecule and the chemist's representation of that molecule in terms of line drawing is quite startling.